Hello everybody, welcome to a Bloedel at IslandWood event. We're really happy about this partnership and we're able to bring you a creative resident from Boedel Reserve, and I'll tell you more about him in a minute. I'm Amy Weber. I'm the Creative Residency Program Manager at Bloedel. And if you don't know about the residency program, it's a program where we bring in 10 to 12 creative thinkers each year, and they can stay for 3 weeks in a house in the woods at Bloedel and work on their various projects, think, meditate, and create new things that they bring out to us and to the world. So we're really happy to be here with Peter. And we're also happy and grateful to the staff at IslandWood who have taken time today to be with us and help us with this, and to the Fletcher Bay Foundation who helped support this program and other programs like this. These programs can only exist with your support. This is the mandatory plug. You guys all know about this, but it is true. We need support in order to keep bringing wonderful, free and low-cost community events to the public. You can go online to the IslandWood site or the Bloedel site and support either one of these wonderful nonprofit organizations. And there's also a little donation box up by the food to help offset that cost if you're feeling generous today. So I wanted to tell you a little bit about Peter. He's a behavioral ecologist, and he's been studying thatching ants for 3 weeks at Bloedel. You can Google him and find out way more than I could ever tell you. And he'll be showing us some of his wonderful photography, an artistic interpretation of his data, and some live ants. So the order of events will be that he will talk and show a brief video. We'll take a break and have snacks, because we all need cookies and water and lemonade. And then he'll come back and we'll have brought out his surprise artistic interpretation, and we'll unveil the ants and he'll tell you a little bit more about them. So without more ado, Dr. Peter Marting, the floor is yours.
Thanks so much, Amy, for the wonderful introduction. And it's such a pleasure to be here in this beautiful state, in this beautiful island. I feel so honored to be invited to this creative residency, and I'm so happy that they gave me a shot. And I've been really enjoying my last 3 weeks here. It's been blowing my mind. I've been having the time of my life, studying ants, creating. It's been really the things that I love most in life. So thank you so much to Bloedel for giving me that opportunity. And thank you so much to IslandWood for providing this amazing venue. I mean, I couldn't have designed a better venue for this particular event. And to have everything set up to be free of cost to the public is something that I really adore. So thank you so much for hosting us. So today, we'll be talking about the Western Thatching Ant. But first, why ants at all? Why are ants interesting? Some of you probably already know ants are interesting, but some might be questioning that. Aside from the fact that you can find them on every continent except for Antarctica, in just about every habitat. And not only that, you can find them pretty easily just about anywhere in the world. You look for a little while, you'll see an ant running around. So they're very dominant and very successful throughout evolutionary history. Aside from the fact that they're incredibly diverse in both form and function, these are just a few samples of ant heads of the estimated 20,000 species that exist on the planet. And aside from their important roles in the ecosystem, they can be incredible ecosystem engineers, tilling up the soil. They can, like leafcutter ants here, can eat more than a cattle in a single day, one colony. And even aside from their complex relationships with other species in their ecosystem, like this ant tending tree hoppers here, or this ant who lives inside of this hollow tree in a symbiosis. Aside from all these amazing things, my favorite reason why ants are so interesting is because from relatively simple individuals, they can accomplish amazing things together without a leader. So this here is a nest cast of an underground nest that ants built. This is amazing architecture, and each chamber has a function, and they need to get airflow down to the bottom chambers. There's this collective metabolism that each chamber takes into account, and there's no designer. Each worker is working simply by following its own little rules to create this emergent property, which is their nest architecture. So I love collective behavior and watching simple individuals do great things. So that brings us to the Western Thatching Ant, Formica obscuripes. First of all, it is just a gorgeous ant. Look at this. I mean, that red head and a black body, such striking contrast. How can you not love it instantly? Here's another shot. Just beautiful. So they're distributed mostly in the western United States, along the Rockies, and they're very abundant around here, Washington State. And I'll just give a little overview about their biology. So they're full omnivores, which means they eat all kinds of stuff, including hunting live prey, like this unsuspecting weevil here. If it's found, they can attack it, recruit their sisters, and bring it back to the nest for food. Not just live prey, but they also scavenge on other insects and spiders and roly-polies that they might find that have recently deceased. And they can collectively transport them back to their nest, like this yellow jacket. Or if it's small enough, they can just pick it up and bring it back, a little snack for later, like this fly. But they don't just eat insects, they also carry seeds and bits of plant material back to their nest to eat, and they chew on the bits of the plants. And it's really fascinating just to watch the ants trail and just see the different things they come back with, because it's so varied. A lot of ant species will kind of focus on one type of food, and you get to see that same thing over and over again. But watching a trail of thatching ants and what they haul back from their hunting grounds is a really cool experience that I recommend. Just sitting, taking 30 minutes and just seeing what you see, what they bring back. They even go after larger animals like roadkill that have recently deceased. And I've even heard reports of some people burying carcasses of animals in the nest and weeks later pulling out clean bones to put on display. So that's a pretty cool feature of these ants. But my favorite food that they eat has to do with this special relationship with aphids. So this is an ant-aphid mutualism, where the aphids, they drink sap from the tree. Now the sap is really rich in carbohydrates and really poor in protein. And in order for those aphids to get enough protein, they have to go through a lot of carbs, and they don't need all the carbs that they go through. So what they end up doing is they excrete liquid that is very full of carbohydrates or sugars. And it's this sugary honeydew, we call it. And the ants drink that right from the aphid, as you can see in this video here. So it's a little hard to see, but I'll show you when a drop comes out right there. So in return, the ants protect these aphids from other insects that might want to harm them, even big things like a person. If you go in and try and steal their aphids, they are ready and willing to attack something as big as a human being to protect their little livestock. So they also pick up the aphids and bring them to the best spots on the plant where they can get their little suckers in the easiest. So the best feeding spots. So they really are kind of like cowboys driving the livestock on the ripe feeding grounds. But one interesting thing that happens with this aphid mutualism is those best feeding spots are often way up at the top of the trees where the newest leaf growth happens. So how do they get that food that they drink from the aphids at the top of the trees all the way down to their nest, which could be a football field away? Because remember, this is not just an individual ant drinking for itself. Ants have their personal stomach, their personal digestive tract, and they also have a social stomach where they collect food to later regurgitate and share with the colony. So what these aphids you're seeing drinking that honeydew, they're often putting it in their social stomach to later regurgitate it. So ants, to get this honeydew all the way back to the nest, ants have different roles that they play. So some are the farmers, the cowboys, the cowgirls, and some are the transporters. So the ants run up to the top of the tree and get that regurgitated liquid and then bring it back down, and they might regurgitate it again to another ground runner, and then that ground runner will get it into her social stomach, and she'll bring it all the way back to the colony to share with the other ants there and the larvae and the pupa. Not the pupa. The pupa are like cocoons. But here's a video of that regurgitation. And in ants, we call this trophallaxis, sharing liquid between two ants. So this is a transporter drinking the recently collected honeydew from another ant. And it doesn't just happen here on the leaf, but it happens also on other parts of the plant. And like I said, even down at the ground. So this supply chain is continuous. So a single ant doesn't have to run that entire distance. So food isn't the only thing that these ants bring back to the nest. If you watch, they're often bringing back sticks, pine needles, parts of leaves, and you have to be wondering, what are they doing with all these things? Some of you probably already know. Now, have you ever gone into the woods and built a fort as a kid like this? You can build something pretty cool, temporary shelter with a group of people. Maybe you can make something a little more complex, last the elements. But what about 100 people? What about 1,000 people? 10,000 people? Imagine the fort in the woods that you could build with 100,000 people. It is a truly spectacular achievement that these ants build their nest. And that's where they get their name, the thatching ant. And these nests can be truly huge. They vary in size from a football to over 2 meters tall in some of the biggest nests. That is huge. That's a huge structure that individuals have made. So why do they build their nest out of this material? The above ground mound is completely made of vegetative material, sticks, pine needles, other things like this. And it's the only ant in North America the Western Thatching Ant who does this. So it's pretty unique behavior. Most other ants that make ant mounds use soil, or at least a mixture of soil and plant material. But the thatching ant is 100% plant material. Here's another shot, a little closer to the nest. And you can see all those little sticks that the ants have brought there. And some of those are pretty big. A single ant can't do that alone. They have to work together to bring some of these bigger pieces back to the nest. There's an ant now, bringing a small stick to the nest. And the other interesting feature about these nests is that they actually clear the vegetation around the nest. They trim the small plants. They use their mandibles, which are their jaws, to clip the growing parts, and they have a spray, an acid spray that they can spray the plants with. And so this clears the space and allows them to really expand their thatching nest. And it also ensures that the nest doesn't get shaded by the sun. So why build your nest out of sticks? It's kind of puzzling, especially if you're the only species in North America who does so. Well, perhaps it has something to do with the warming of the nest. Perhaps that material holds on to solar radiation longer than soil does. And maybe that's a good insulator. So why would you need to warm up your nest? Well, let's talk about incubation for a minute. Some animals, like warm-blooded animals or endotherms, they need the right temperature for their embryos to develop, or else they don't develop correctly. For ectotherms, like ants or cold-blooded individuals, that temperature increase speeds up their development time. So the larva can turn into a pupa sooner. And ants are what we call full metamorphosis insects, or holometabolists, which means they change from something completely different, like a little grub larva, into an adult worker. Same thing as a butterfly. A caterpillar goes through a chrysalis, and in this stage here is the pupa, which is equivalent to a butterfly chrysalis before it turns into an adult worker. So we decided to look into this, why these nests are built like this, and if their temperature has something to do with it. So we developed a hypothesis about what we might find if we look inside the nest versus outside the nest. So throughout the day, the time of day is on the x-axis on the bottom, hours in Army time here, and temperature is on the y-axis. Of course, throughout the day, the temperature rises, and as sun sets, the temperature falls, and that is the daily cycle. And so what we guessed with this insulating material, the ant nest might do over the course of the day, is something like this, where it's a little behind the daily temperature. It rises a little slower, but then it gets to hold on to that heat for longer into the night and keep that incubation a little longer than the day cycle would allow. So to test this hypothesis, we went out into the Boedel Reserve and found 5 ant nests to measure. And we inserted a thermometer into the center of these nests, and then we had a thermometer on the outside. And we basically checked that temperature for every hour in a 24-hour period. So we didn't check all the hours of the wee morning, but we collected at 11:30 midnight, and then again at 4:30 in the morning to get a nice round idea about how these temperature changes over this cycle. And one thing we saw while we were out there was these ants carrying their pupa, not on the inside of the nest, how you might predict, but carrying them from the base of the nest on the outside, bring them all the way to the top of the nest, and then going back inside the nest on the top. And so we measured that too. We looked at, okay, how many ants are carrying pupa at every sample we took temperature, so every hour of the day. And so a pupa run looks something like this, where an ant appears at the base of the nest, and she runs up, maneuvering across all the sticks, and enters back into the top of the nest. So, what did we find? Let's look at our results for the pupa first. So, the temperature is now on the x-axis in Fahrenheit, and the number of pupa carried on the y-axis. And so the temperature, this is on the inside of the nest. So there is a correlation there with the warmer the nest, the more pupa carried, but it's not a super strong correlation. We found a stronger correlation with the outside temperature. So the temperature outside gets warmer, there's more ants carrying these pupa on the outside of the nest. Our speculation of why this relationship occurs is because the ants on the inside of the nest, imagine the labyrinth of sticks and tunnels and chambers that you have to traverse if you're trying to take this packet of pupa up to where it needs to be. That probably takes a long time. But if the pupa cools down enough, then that's bad. You want your temperature to be high. So basically, while they're inside the nest, the temperature is warmer, so they bring them inside the nest. But once the day gets warm enough, then the ants take the pupa on the outside, and it's basically a shortcut because they don't have to maneuver this labyrinth of internal nest structure. So let's talk about the results of the temperature inside the nest versus outside the nest. So this is the external temperature, the temperature was outside, what you might expect, a normal day, maybe cloud cover in that middle of the day, drop the temperature down a little bit. And then let's see if that temperature followed the outside temperature for the nest. Not even close. Not even close. There was no overlap in the temperature inside the nest versus the temperature outside. 85 degrees in the coldest parts of the night. 85 degrees inside the ant nest. And this is one colony, so maybe it's a fluke, maybe what's going on there. So let's look at all the colonies together. Look at this. All 5 colonies. Their nest is between 83 and 86 degrees throughout the coldest parts of the night. And that is really warm. That is astounding. I mean, let's talk about this for a minute. Remember, an individual ant is cold-blooded. It has no way to generate heat like warm-blooded individuals. But the nest can thermoregulate. The nest, the collective, is like a warm-blooded superorganism made up of cold-blooded individuals. That is mind-blowing. So how do they keep their temperature stable? How do they do it? So I have 5 hypotheses here. One is that, yes, from metabolism, ants do generate a little bit of heat. It's nothing like we generate, but just the process of metabolizing their food, a byproduct is heat. And so getting enough ants together, you might generate a bit of heat, but that does not account for the 85 degrees inside the nest. The other hypothesis is that solar radiation helps heat up that insulated nest material. And that nest material really does hang on to the solar radiation. But that's not all. How about, because this is made entirely of vegetation, the microorganisms that live inside the nest function somewhat like a compost pile in that they generate heat themselves. But this isn't so simple because a compost pile is the Wild West. Any microbes, have at it. But an ant nest is a very carefully controlled ecosystem. Those ants can't have any wild bacteria in there. They would start eating their babies, their larvae. They would decompose the sticks, things would fall apart, and it would turn into a big pile of mush in a couple of months. But these nests persist for years. So the bacteria have to be very carefully maintained. Kind of like park rangers, very carefully maintained species. Another interesting hypothesis is the idea that these ants have black bodies, and on cool spring mornings, they run out of the nest, find sunspots in the forest, and sit there and let the sun warm their little black bodies. And then the ants run back to the nest, all warmed up, and they enter the nest, and their heat gets distributed. And they run back out and heat up again and do this over and over. With a couple thousand ants doing this, you might heat up a nest in no time. So the fifth hypothesis, and this is maybe my favorite, and the one we kind of looked into a little bit. If you look closely, the ants on the top of the nest, they're not just setting the sticks there. They're moving them. They're constantly rearranging those sticks on the surface. And so could it be that they are basically rearranging their house, the roof of their house, to collect the right amount of solar radiation throughout the day, opening entrances, closing entrances, shifting this modular architecture around so that they maintain a stable core temperature? I think that's a kind of exciting idea, but it's sort of hard to see the pattern of the sticks moving around just by looking at real time. So we decided to try a time lapse. Let's see what these sticks do if you look for a few hours. So, as you can see, there's movement. There's pebbles. There's sticks. They're shifting around. But again, it is a little hard to see the pattern with the naked eye and these sticks. So we decided to use toothpicks, colored toothpicks, individually marked so we can track each one separately and see where it goes. So here we go, setting these toothpicks on the top of the mound. Let's try this again. And look at this. They took those toothpicks and they kicked them right out of there. But wait. There was a nest about 3 feet south of here, like just out of the frame. All of the toothpicks ended up there. So they were like, we don't need these sticks here. We need them down in the South Colony. Get them over there. Stat. So we did it. We're like, let's just move the camera. What's going on here? So now let's watch. This has 10 because we added toothpicks to this one too. And they brought the toothpicks from the north nest just down. So here you can really see how much these toothpicks are moving. If you watch an individual toothpick, they're moving all over the place. And this is hours. And not just hours, days. These toothpicks moved around this nest for about 2 weeks, shifting throughout the day. So that is a crazy phenomenon right there. And with the scope of these 3 weeks, we weren't even able to analyze all the data. We've got these we have to track the toothpicks. We have to see how it correlates with the temperature. It's going to take some time. So we needed deeper analysis of this toothpick. But clearly something's going on, and it's not just a simple, straightforward pattern. Like in the afternoon they bring the sticks to the south, and the morning they bring them to the north. It's more complicated than that. It might be more finely nuanced. Question. Yes, they didn't. They weren't incorporated into the structure of the nest for at least days, weeks even. We did show up later at some nests, and we did see these toothpick just ends sticking out of the nest. So it might take some time. It might be a pheromone that they laid in the sticks with. What position or orientation they arrange the sticks throughout the day. Does it have to do with the sun? Does it more have to do with blocking particular entrances of the nest? Because you need airflow in and out. One thing that we weren't able to capture, which would have been amazing, was unfortunately that really hot day a couple weeks back. We arrived on that day, and didn't even know what we were doing yet. But it would have been really interesting to see if they could cool their nest. Because so far we've seen that their nest temperature is well above any part of the day that we've measured. So what happens if the day gets above? Do they have mechanisms to actually cool down the nest? And does shifting those sticks, maybe opening up those entrances wider, have anything to do with that? We just took one measurement inside the nest, unfortunately, but I would love to know that. Absolutely. So one way that other ants get the right temperature for their larvae is they build nests in the soil, and maybe they build a mound, and they collect solar radiation like how I would have expected, how I hypothesized. And then throughout the day, there is this temperature gradient throughout their nest where it's warmer on top and colder at the bottom. And there's a sweet spot for each developmental period of each larva. So the ants, as that gradient cools down and heats up, they have to move all of their larvae to the sweet spot, up in the day, down at night, or vice versa. So there's a lot of energy spent moving ants around, moving larvae around. And so I think something similar is happening here, where there is probably a gradient inside these thatching ant nests anyway, because they have a stable core temperature, but their nests also permeate the ground, and they go deep underneath the ground and are probably a lot cooler under there. And so it could be that the pupa, say, for example, need the highest temperature, and the highest temperature happens to be at the top of the nest. Well, I think those ants are probably carrying those pupa up to the right sweet spot. But here's the thing, is the sweet spot for the thatching ants is always the same spot, probably, versus other ants where that is a moving target and they have to move throughout the day. Yeah. So yeah, there seems to be large empty chambers. Well, not empty as in devoid of anything, but spacious chambers inside, using those sticks as infrastructure to hold up the thatch. I imagine it would be lower. I imagine it would be lower. I think they actually do hibernate. Like honeybees, for example, honeybees don't actually hibernate. Because an individual bee can heat up. It can activate or flex its flight muscles. And that flexing can actually generate a good amount of heat. So in the wintertime, bees are awake, alive, and well, and just very warm inside the center of their nest. But I don't think, I'd be surprised if thatching ants could achieve that in the winter without that being able to generate heat themselves. But an interesting thing to measure.
Can you tell yet? I know you have to.
Oh yeah, we don't know yet. Yeah, that's an exciting direction. It could be that an individual stick ends up in the same area at a certain time of day. But yeah, we just haven't gone that far. What's that?
Can you tell how they communicate with the girl?
That's another great direction of research. I mean, this is exactly the questions that I have about this phenomenon.
And seeing what Bloedel had to offer.
You know, I'm glad you brought that up. So my original proposal included the first few days of scouting what species of ants are here. Because I'm not from the area and I'm not familiar with the fauna. So that was going to be the first few days, and then we had all this other things planned, and we had no specific research question. But luckily, Amy, she, the creative coordinator, she was on the ground scouting out the ant nests before I even arrived. And she actually sent me photos of some of these thatching ant nests. And she's like, "This is great. You're coming in July. Check out these nests, these ant nests." And I was like, "Oh, this is amazing." Like these ant nests are incredible. They're huge and very conspicuous. So you can't miss them. So very easily identified the species just from the photo that Amy sent. And from there, started reading about what's known. And it wasn't until a few days of deep observation after we arrived that we decided to go with the temperature analysis. So what we've learned here illustrates my favorite reason for studying ants, is that relatively simple individuals can achieve greatness together. And in this case, a group of cold-blooded individuals create a warm-blooded superorganism. So with that, I'd like you to ponder on that a little bit, let it percolate. And I really want to thank my partner, Michelle Simpson, who has been not just an assistant for these 3 weeks, but a true partner in that we're coming up with these designs together. She helped a lot with the art piece, the video, all the pieces. She's been an essential role for this. So we share credit for this endeavor. So please thank Michelle. And I'd also like to thank, of course, Amy, who's been amazing and provided all the resources that we needed, and then some, and all the Bloedel staff, Bob, Sean, Joe, the IslandWood staff for having us, especially Amanda and John. This has been incredible. So with that, and thank you all for coming. This has been a wonderful audience. Thank you. Yeah. So we have a few more things. That concludes the presentation portion. So upcoming, we have a 7.5-minute mini documentary of sorts. That's, oh, we have a question. Go ahead.
What do thatching ants eat?
Oh, they eat everything from dead insects to live insects, seeds, honeydew from aphids, all kinds of stuff. Cheerios, I'm sure. So I have a 7.5-minute documentary here, which it's more of an experiential documentary. There's no voiceover. It's just images of the concepts that I've just spoken about. So just sit back, relax, and enjoy the majesty of these Western thatching ants.
And that will be followed by snacks and the art piece.
Yes.
And the ants.
Yes. So then after the documentary, exactly, we'll bring out the art piece that was inspired by the data and is in fact encoded with the data. And then we have live ants on display in the back. this is the piece here. There are a couple layers here. So first and foremost, this is a representation of the thatching ant nest. And the LEDs are encoded with the data that we collected. Colony 4, to be exact. These are the actual numbers that you're seeing here. So the color, the main color inside the nest itself is, the color inside the main nest itself and the ring around the nest are both calibrated so that the color equals the temperature. And as you can see, the warmer temperatures denote warmer colors. So as you can see here, the LEDs around the outside never quite reach the same warmth of color as the LEDs inside the nest. And that ring around the outside represents the path that the sun takes. And in particular, the path that the sun took on July 1st when we collected this data. The angle is set to 65 degrees off the north axis, and that cycle, that ring is basically rises and sets at about the same angle that it did on that particular day. So you can watch the sunrise here, and as the sun rises, you can see the days heating up as that sun is changing colors. And you can see there's a moment here where inside the nest gets pretty warm, right there. But then it cools down as the sun passes. So there might actually be doing some cool down mechanism inside the nest. We're not really sure. And then finally we have the white LEDs that are traveling from the base to the top. And who can guess what that is?
What are those ants bringing the little, I can't think of her name, pupas?
Pupa. You got it. So as you can see, the pupa are carried to the top throughout the night, but it peaks in the late afternoon. And you can see all this activity of the pupa brought to the top. And so the other layer to this is it kind of looks like some sort of hairy mammal. And that is not by mistake, as we know mammals thermoregulate. And so this is sort of a representation of an ant nest made of cold-blooded individuals thermoregulating as if it were a mammal.